Hey everyone. So today I'm going to be teaching the two pointers coding pattern, and this pattern is very common in regular interviews as well as lead code. So understanding this pattern is key for solving a ton of questions optimally. This is why I wanted to teach it. So what exactly is the two pointers coding pattern? So yeah, pretty much it's when you have two or more pointers to indices in some data structure, and it doesn't even need to be indices, it's just two pointers in general, pointing in different areas in a data structure, but a lot of times it's an array. And then yeah, you traverse these pointers through an array, either moving the same direction towards the center or moving away from each other, and I'll show examples of all the different ways that you can move pointers across a data structure. But yeah, mostly these two pointer techniques are used to solve questions optimally without using extra space. A lot of times there will be algorithms where you could solve it without using two pointers, but you'll need to introduce a hash map or another data structure. But then yeah, that introducing a hash map or another data structure usually increases the amount of space you need. But when you're working with pointers, you just store variables, two variables, sometimes three variables, four variables. I'll show an example of when you have to have three pointers. But yeah, since you're only storing pointers, your space complexity is basically O of 1 instead of O of n. So it's like you could take solutions from O of n to O of 1, and some companies actually really want you to get to these space optimized solutions. So yeah, so what I mentioned is depending on the problem, the pointers may move in the same direction, towards each other, away from each other, etc. Let's look at the first one where pointers move in the same direction. Pointers moving the same direction is usually common for linked list cycle detection and other ones such as removing duplicates in an array. And I'll actually write out the code for how to remove duplicates in an array using two pointers to move in the same direction. But let me visualize some of these different ways you can move pointers. So pretend we have a linked list, and this is when we want to move pointers in the same direction, and we want to detect if there's a cycle in a linked list. How do we do that? Well, one way is to create a hash map of all the nodes that we've seen, and yeah, essentially create a hash map. And for pretend there's node 1, node 2, node 3, node 4, every time we see a node, we mark it in the hash map. For example, if we were traversing here, we'd be marking all the nodes in there. And then suddenly when we get to 2, we see that it's already in the hash map. And we say that there's a cycle because we visited a node that we've seen before. But you can see this hash map requires extra space. It actually takes O of n space because it could take up all the nodes. You can see there's 4 nodes here and there's 4 elements in the hash map. Pretend we have 50 nodes. And the cycle is only introduced at the very last node. Then the space uses basically 50. It scales linearly with the length of the linked list. But how do we do this without using any extra space? Well, like I mentioned, we could just maintain variables, the two different pointers, and these are just two variables, and we move one really fast. Specifically, we make one move 2 nodes at a time, an iteration, and one lag behind it by moving only 1 node at a time. So how that look? Say this is our fast pointer, we make it move up 2 nodes. This is our slow pointer, we make it move up once, right? Then on the next iteration, we make this fast pointer move up 2 nodes, and then the slow pointer move up once. And then again, we make the fast pointer move 2 nodes, 1, 2, and then the slow pointer move once. And you can see if they ever, after an iteration, if they ever end up at the same node, then we have a cycle in the linked list, and that's actually how you are able to detect cycles in only O of 1 space. See, it's kind of a neat technique, but you can see in that example, we're moving pointers in the same direction. let's go to the next one. Moving 2 pointers towards the center. This is usually done when we're trying to find a pair of optimal elements in a sorted array. So, and it doesn't have to be a sorted array. There's other questions where you want to move 2 pointers. You put 2 pointers at the different ends and move them towards the center, such as trapping rainwater. And yeah, you just need to make sure that the array is structured. Most of the time, you're just solving questions where you're trying, when it's asking, oh, find these 2 elements that maximize some result or hit a specific result. And yeah, let's look at how we would use 2 pointers in this. So if you're looking at this question, it pretty much just looks like the basic 2 sum, where we're given an array and we're trying to hit a specific target, which is 10. But the one thing is, this array right here is sorted, so we can do something more clever with 2 pointers to optimize for space and get O of 1 space instead of the regular O of n. How we would do this with a hash map is you pretty much create a hash map, and as you iterate through the different elements here, you just store the different elements that you've seen. 1, 2, 4, right? So eventually when you get to 6, you check, okay, the target is 6. Have I seen a 4 before? Yes, I've seen a 4. What's the index? And then you're able to get to the target. But with the same rationale as the linked list one above, this is going to take O of n space. But yeah, how can we can optimize that with 2 pointers from just the simple fact that our array here is sorted. So pretend we're looking for a target 10, right? We know that since this is sorted, we know that pretty much if we move this left pointer to the right, we're only going to increase the value here, right? Because 12 is well, this pointer is stuck on 12, so if we move the left pointer, since it's increasing, the value can only go up from here. So when we move it, it'll turn to 14. If we move it here, it will turn to 16. And then, but we also know if we move our pointer stationed here to the left, it'll decrease the total value of the 2 indices here. So if we're looking for the target of 10, and right now the 2 indices make it 13, if we want to get to 10, well, we have to move this right pointer down to get a smaller value. And then now, what do we have here? We have 7. Okay, now that we have 7, now the value is too small. Now we need to move our left pointer up to get to a higher value. What value we get now? 9, or sorry, 8. And then finally we move it up again, and you could see 10, and you could see that we're actually able to find the 2 elements with just O of 1 space. So that's when you're moving 2 pointers towards the center, right? You station them at the left and right, and then you move them towards. And then lastly, how do we check? We can also have an approach where we have 2 pointers and we station them at some index, and then we move them away from each other. Usually we do this when we're trying to check for palindromes. So let's start here. Let's say, see, both of these pointers point to the same value, so it's a palindrome. Let's turn this into a palindrome. Then we move the left one back and the right one forward. Are they pointing to the same value? Yes, so it's still a palindrome. Then we increment them. We decrement one and increment the other. Are they pointing to the same value? Yes, so that string is a palindrome. Pretend that this was a X here. Is C a palindrome? Yes, because the 2 pointers have the same value for now. But then when we move the pointers, we see that there's a mismatch, and we can say that this string is not a palindrome. So that's one way that we can move. We can use 2 pointers to check if something is a palindrome. Yeah, and that's pretty much the brief walkthrough there. Let me actually go through some examples to make it more clear for everyone. So this is the first question that I want to walk through. We're given a sorted array of numbers, and we have a goal of moving all of the unique numbers to the beginning of the array. By unique numbers, I mean pretty much pushing all of the numbers that are duplicates to the back, and just keeping one of the elements around. So you can see we have this array. Some are duplicate 1, 1, 2, 3, 3, 4. In the output, we should have 1, 2, 3, 4, the unique elements, and anything that's duplicate, push it to the back. So the first 4 elements will be 1, 2, 3, 4, and then we don't care about the rest of the array. So yeah, we want to actually do this without using any extra space. So don't build a copy of the array. And yeah, when you hear extra space or no extra space, you should start thinking of how can we do this with pointers. So how could we actually do this with pointers? Let's say we position a left and a right pointer. Let's say we're gonna have a left pointer equals something, right pointer equals something. Our left pointer is basically gonna tell us the next available index. And then our right pointer is going to look for elements to send to the front, right? So pretty much left is the next available index. When we start, this index is available, and we need to look for elements to send to the front of the array or to the left of the array. How do we do that? Well, one, what elements do we want to send to the left of the array? We want to send pretty much one of each, because we could have multiple, like 3, 3, 3. We want to return just one of each of these elements. So 1, 3, 1, 2, 1, 1, 1, 4. So the way I'm going to do is I'm going to send the last element of a series of numbers to the front. So how do we know if something is the last element? Well, with the right pointer, we just check to the right. Is the element to the right the same value as me? So yeah, 1 is equal to 1, so we move forward. Now we check it again. Is my right element the same element as me? No. So let's send this element to the back. We kind of do a swap here. It's kind of a no op, but yeah, now the next available index is here, and we move this after doing the swap. Now we ask it, is the element to the right the same as my value? No. So this is so we want to send this to the back. We move this up. Then we go right here. Is the element to the right the same? Yes. Is the element to the right the same? No. So we swap 3, 1. Now we're at the end of the array. The end of the array will always be the last element in a series of values because it's just the end of the array. So, I mean, we move this up one. So we just swap that. And you can see we're able to move all the duplicate elements to the back without using any extra space at all. So let me write up the code for that. So let's say move duplicates to end. So we're given nums, and we want to return in place the numbers there, or we want to modify the array and then return that array back. So let's start with the left and right pointer, and they both start at 0, and this is the case when we have two pointers moving in the same direction. So yeah, let's go back to where it was before. 1 1 1 1 2 3 3 4. So the right is looking for elements to send to the left of the array. So the right will always progress further. So we'll say while the right is less than the length of nums, we keep the iteration going, and then we increment this right pointer. Like I mentioned, if we're at the end of the array, that's always the end of the series. So if the right is equal to the length of nums minus 1, or because if it's we always want to send to the back, or nums at right is not equal to nums right plus 1. So if it's not equal to the one beside it, then we send it to the front. So how do we send it? And then how do we send it to the front? Well, we do a swap of those elements. So we say nums left, nums right. So we do a swap here. That's how we swap. We take the right, move it to the left, and we move the left and move it to the right. And then we increment this pointer. Yep, and then we increment the left pointer. And I think that should do the trick here. Let's actually test it. So let's print, move duplicates to the end. We're gonna be given this array right here. And what we expect is this result. Yep, you can see it move. Yeah, where is it? Yeah, you can see that we get the right result there. If I was doing this in the interview, I would run something like this I would write a unit test to show that it works correctly. So I'd assert this equals that, and then be like print success. If it hits success, then it works. Pretend we had a bug here when we were moving right like +2. We can see we get assertion error because it doesn't get to the right result. Yeah, that's pretty much how you do it. And yeah, I just want to point out the reason this is also important where we do this check first before this one, because we don't want to be checking to the right when we're at the end of the array, because that will lead to out of bounds index error here. So I positioned this check before in the OR because it'll early return here. The moment it sees it's at the end, it won't run this statement. That's subtle things that you could do to make your code better. But yeah, that's question 1. So let's look at question 2. We're given a sorted array of numbers and we're looking for a target sum. And I mentioned this a bit in my intro here. This is when we have 2 moving to center, but I'll show how to actually code that up. So yeah, essentially we're given a sorted array of numbers and a target sum, and we need to write a function that returns the indices of 2 numbers that add up to the target. It's essentially 2sum, but since the numbers are in a sorted order, we can write a more optimal algorithm when it comes to space using 2 pointers. So yeah, how do we do that? Like I mentioned, we're gonna have a left and right pointer. One left, one at the very start, the left at the very start of the array and the right at the very end. And we're gonna move them together based on some conditions. So let's create this function, target sum. We're given nums and we're given a target, and we are assuming that nums is in sorted order. So let's start with a left and right here. We say left starts at 0 and right starts at nums -1. So what do? We're given, it's a little bit weird, but yeah, we're gonna say while left is less than right, because we're bringing the 2 pointers in towards each other. We say while left is less than right because if they're pointing at the same index, we're trying to return 2 different indices. So we don't really want them like pointing at the same index. So while left is less than right, we're gonna perform some logic. Let's grab the current sum equals, we'll say nums of left plus nums of right. So what's the current sum of 10 plus 1? That's equals to 11. So we say, first of all, if the current sum is actually equal to the target, we'll just return the left and right, because that means we got to a result. If left plus right, 10 plus 1 is 11, is actually if the current sum is greater than the target, How do we make the value lower? Well, we move the right pointer down. Else, pretend the current sum is less than the target. Then we want to move the left pointer up to generate a bigger value. So do left plus equals 1. And yeah, hopefully we return the result. Worst case, it's not in there, and then we just return -1, -1. So yeah, let's do print target sum of this right here. And if we want to look for 8, you see we get 1 and 3. Let's just write an assertion here like I mentioned. Assert so we're saying that should equal 1 and 3. No errors. What if we have a different target of, say, 16? That should equal index 1, index 0, 1, 2, 3, index 3 and 4. So it's something like this. And then we just print success. So yeah, you can see right there, that's how you solve this problem of target sum. And you can see right here, we only use O of 1 space because we're just maintaining 2 numbers. And the runtime, this is space, and runtime is just O of 1 as well. Or sorry, not O of 1, O of n, because we like for each iteration, we move an element, either increment one of the pointers or decrement one of the pointers. So they eventually only traverse each iteration. It traverses one element, and yeah, like worst case, the elements meet up and it would have traversed the whole array. Even if it was in the middle, you could see that like if you combine the distance of how much each of them traveled, it's equal to the size of the array. Yeah, that's pretty much all I want to get for that question. This next question is a pretty fun question. We're given an array that contains only 0s, 1s, and 2s, and we need to move all of the 0s to the start, all the 1s to the middle, and the 2s to the end. So we could actually solve this, and we want to solve this without using extra space. I mean, you could solve this by creating a copy of the array and then building up the array. Yeah, like if we create a copy of this array, it would be possible, but that would be using extra space. But the way to actually we can solve this using 3 pointers actually. So we can have a left pointer, a right pointer, and a middle pointer. So we station one at the left at the start and the right at the end. So the left will be next available area for 0, because you can see like what we want to do is push all the 0s to the start, push all the 2s to the end, and keep the 1s in the middle. So left will tell us the next available area for 0, next available index. Right will tell us the next available index for a 2. And then finally, mid will pretty much iterate through the array. Will iterate through the array looking for values to swap. So if we start mid, and mid will iterate through the array looking for values to swap. So we start with a 2. We see that it's a 2, so we need to swap it with the next available index for 2. So 2, we swap it here. We decrement right. Now it's looking at a 0. It needs to swap it with the next available index for a 0. So it does the swap, but it just swaps in the same spot. So now we could increment the left because that spot is now, like we just moved the 0 there. And then now the mid is looking at a 0 again. it performs another swap right on the same index, but we can move the left index up because now we place a 0 there, even though the 0 was already there. Now we see a 2. What are we gonna do? We're gonna take the mid and swap it with the right. So we do 2, 1. We get here. And what we're basically, we can stop it. We'll say while, now the mid kind of equals the right. Now they're pointing at the same index. So yeah, if we need to, now we know all of these are in the right position. And yeah, there's pretty much nothing to swap to because M is at right. But we probably want to do one more iteration in case this is like a 0 or something. We want to swap it. So you gotta watch for edge cases there. So let's just implement this now. Let's call move or partition array. And we're gonna be given an array of nums, and we want to do it in place. So we're given a left pointer, a right pointer, and a mid, and we say the left starts at the very start of the array, and then right start at nums -1, and then the mid starts at 0. So that will position all of the elements like this. Now what do we want to do? We want to do a while loop. We'll say while right is less than while the mid is less than equal to the right, because we're moving the mid, and once it reaches to the right pointer, once it crosses, we shouldn't keep iterating, and we'll be incrementing the mid, or we'll see. Let's see. Let's not increment anything right now, but while basically if nums at mid is equal to 2, what we're gonna do is we're gonna perform the swap. So we'll say nums mid. So we'll do the swap. We'll say nums right goes to mid. Nums right goes to mid, and the mid goes to the right. And then we'll move the right, we'll decrement the right. And yeah, that's because the next available one is there. Let's see, it's 2, 0. Does a swap. 2. elif the nums mid is equal to, if it's equal to the 0, what we're gonna do is we're gonna swap the mid with the left instead. So that's what we're doing here. And then after we swap that, we increment the left, and then we also increment the mid. And then lastly, pretend we're just at a 1. Pretend we're at a 1 here. We have pretend 1, or we're here 1. We just want to leave it, or we do the swap here. Pretend we're at a 1. We just want to leave it alone. So we'll just increment mid plus equals 1. So that's how you partition array. Let's actually verify that this works. Let's say partition array, and we're going to be given we want it to eventually be partitioned like this, and then let's play around with moving the elements around a bit. Okay, run this. Do success. Right. Let's play with moving the elements around a bit. 2, 0, 0, 1. So yeah, this is a interesting example. So this 1 should get to the middle, and then the 0 should end up to the left, and the 2 2's should be end up to the right. So let's run that, success. And like we can print what this will return. See, partitioned it correctly. Yeah, that's a pretty interesting problem. Those are the three questions that I wanted to quickly go through. And yeah, let me close it off with the common mistakes, common pitfalls people make when doing two-pointer solutions. The first is not comparing or moving the pointers properly. Make sure that you're doing the comparisons correctly and you're moving the pointers accordingly. So pretend when we're looking for optimal elements in a sorted array, when we have one over here, one over here, if your comparison is wrong and you're maybe moving the left pointer when you don't need to, or moving the right pointer when you need to, you mess up that condition. For example, if the target is right here, the target is 13, or target is 10 and here's 13, and instead what you do is increment the left, you know you're gonna reach a bigger number and you'll never find the result, and that's an error that you can have. So make sure that you're moving the pointers in the right direction and doing comparisons correctly. Index out of bounds errors when accessing the start and end of the elements. I think I covered that in the second question. And yeah, failing to handle corner cases with smaller empty arrays. Make sure you can handle all the corner cases. Try it with smaller empty arrays, and then yeah, make sure you're incrementing or decrementing the pointers on each iteration. Otherwise, you're going to end up in an infinite loop. So yeah, that's pretty much everything you need to know about the two pointers. I hope this video was helpful, and I'll see y'all in the next video.